And after looking at sample sums, we're going to take a look at sample means. And this is a short but important section because it connects with ideas that are actually very, very much used in practice. And the reason is that population-related ideas are mostly theoretical because we're talking about having the entire distribution, being able to draw arbitrary samples from them, knowing the distributions. But in the real world, what we deal is with samples of data. We actually have whatever data set we have in front of us is finite, and it is a sample. It is not the entire population. It is not an abstract mathematical object. It is a set of numbers, right? And so we want to learn what happens when we look at finite samples. We still draw upon our understanding of the underlying distributions, but we now want to make conclusions about finite samples. And so we've just looked at the expectation and standard deviation of the sample sum. Now let's ask what happens to the sample mean. So the reasoning is very similar. I'm not going to actually repeat the algebra. What I want you to do is connect in your head, and if you have any discomfort with your specific formulas, grab a piece of paper, pause the video, and do it yourself. It's really the same thing we've been doing over and over, so I don't want to keep doing more of that. I think we've done enough of that. So let's think of, again, a situation where we have n random variables that are all IID, and again, for each of them, the expectation, their expected value is the same, their means are mu, and their standard deviation is sigma. So the sample sum is the sum of the xi's, and the sample mean is the average of these. It's 1 over n times the sample sum. Since it is just a straight up simple linear transformation of the sample sum, scaling it by 1 over n, as we know, therefore, the expectation of the sample mean is going to be the same value, mu, and the standard deviation is going to be equal to the original standard deviation divided by root n. Just as we saw before, the same exact algebra applies, and we have these expressions for what happens to the, based on having n IID random variables, what happens to the expectation and standard deviation of the mean of those n random variables, which is exactly the kind of thing that we have in data sets. This is not a purely kind of theoretical construct. As we said, imagine you're thinking of asking what is the average height of undergrads at Berkeley. You go out and you decide how many you're going to sample. You think about your sampling strategy. You make sure that you don't do it in a single building because you'd be probably sampling all from the same subpopulation. You'd introduce a lot of bias. Maybe you walked into the basketball gym and you're sampling from the basketball team, and therefore obviously that would be a poor way of getting data about the entire undergraduate population. But whatever you do, even assuming that you do a great job with your random sampling, you have a single average, right? That sample gives you a single mean. If you had done it a different day, you would have bumped into different people, or if you had walked across campus in a different order, right, you would have gotten a different set of people. And so, in general, what we want to ask is, what would happen if you could do that many times? What is the distribution of possible means? How is that one mean that you get related to the population mean if you could do the experiment infinite times, right? And so, as we've seen, the expected value of this sample mean is mu. Mu was the population mean, right? So what this is telling you is that the expected value of the mean that you get is correct in a sense. Statistically, we describe this as unbiased. Now, we're not going to, this is not an in-depth technical statistics course. You will see more of that. We'll see a little bit more of that later in the semester, and these ideas are covered in more detail in your stats courses. But the point is that when we obtain this result, a result of this kind that says what I do with one sample, the quantity that I can compute from the one sample of data that I actually have, right, which is only one, is actually, in expectation, is actually the correct quantity that I would have if I had access to the whole population. We say that quantity that I'm computing is an unbiased estimator, meaning it doesn't mean that it's correct because this is an expected value, right? Any given value that you get may be a little bit different, but in expectation, it is the value from the population. So it doesn't have a built-in shift, a built-in error, a built-in bias, and this is why we use the term unbiased. As you can imagine, in general, we tend to look for unbiased estimators. But the point is, this is thinking about distributions, right? And so now the question that we have, we already know that the value that we get from the sample mean is the population mean, so this is great. But we know that when we get one sample, it may not be correct. Like we may not get mu. We may get mu plus or minus something. Well, plus or minus how much? What happens? How far off can we expect to be in general? And you can't repeat the experiment an infinite number of times. But what you can do is ask yourself, what happens if I collect a little bit more data? Right? What happens if my sample size is a little bit larger? Right? How much improvement? What happens to my error? Right? Around my expectation value is the correct value mu, but any one value that I get is going to be a little bit off. But if I collect a little bit more data, how do I improve? That is a really useful and important question, right? Understanding what happens to your error if you collect more data, because that gives you a sense of how much is it worth to collect a little bit more data, right? And in general, the calculation that we just did tells us exactly the answer to this question. You've already seen this in Data 8. We call it the square root law, but we just proved it using the machinery that we've been developing in this lecture. We see that the standard deviation of the sample mean is sigma over root n, which means that as we make n bigger, the standard deviation of the sample mean goes down like 1 over square root of n. And this is illustrated in this plot, which I'm going to try to explain for a minute, because it's important that you actually convince yourself that you understand what this figure is showing. What we're showing here are the distributions of two sample means drawn from the same population, but with different sample sizes. So the blue histogram is the histogram of drawing. We have a population and we draw a sample of size n, and we do that over, and in this case this is a theoretical experiment, right, to show you what happens. So we draw n times we draw samples of size n many times, and we plot a histogram of all those samples of size n, and that's the blue histogram. And then the yellow one is the same thing, but with a different value for n. Let's call it n prime, that is bigger. So if each individual sample, the point is each individual sample in the yellow histogram is bigger than in the blue histogram. But both of them are drawn from the same population, which means they're both targeting the same mean. However, the bigger samples produce a population that is narrower around the correct value, around the population value. Now, in practice, you're not going to build this histogram, right? You will have one sample. When you do a survey, you have one sample. You don't have a population of samples. You have a single sample. But the point is, if one of your samples is in the yellow, from the yellow group, it has a higher chance of being closer to the true value than if it's in the blue one, where any one of your sample has a higher chance of being further away. How they're related is this factor 1 over square root of n. So this basically tells you how much do you win by making n bigger, by making your sample size bigger, by going into the yellow sample, into the yellow regime that has a larger value of n. And this is finally, to wrap this section up, connected to the central limit theorem, which you have already discussed a little bit in Data 8, and which Prop 140 goes into in a lot more depth. We're not going to discuss the central limit theorem or use it in that much detail in this class, but the point is that the central limit theorem tells us that the probability distribution of these sums of IID samples is approximates a normal distribution as the sample size is larger, which is pretty much what we're illustrating here. Now, a nice full intuitive description and presentation of the central limit theorem, which is really a key result in statistics, is more than we have time for today, so we will leave it at that. But we might add a little side lecture on the central limit theorem, which is kind of a fun topic. But in Prop 140, it is discussed in quite a bit of depth, and so you can also go there for reference for some of those lectures.